So, a rate problem. So here's, before we do this problem, just like when I talked about digits, I want to do some background and make sure we have, how to deal with this. So with rate problems, there's kind of two situations. The two types of problems are, you got a boat in the water, and if the boat's going with the river, if it's going with the river, then it's going to go faster. If it's going against the river, it's going to go slower. Same thing with a plane. Like if a plane's got a headwind, the plane's slowing down. If the plane's got a tailwind, it's just going to go faster. So when we're dealing with any of these rate problems, there's either wind or current impacting how fast the object is going. Now, before we even set this up, let's make sure we remember one thing from physical science, and that one equation that we're going to pay attention to from physical science is rate times time is equal to distance. All right, this is huge. This is the equation we're going to use. Rate times time equals distance. All right. Now, I want to go even further because I like my chart. And in this particular problem, I have two things going on. I have two situations. I've got one where we're going upstream. I've got one where we're going downstream. And here's how it works. Since I've got two things, I've got a rate, and I've got a time, and I've got a distance. And so this is, I'm going to say this is down. So this first row is talking about going downstream, and the second row is talking about going upstream. And if we look at, so now let's read the question. It says a motorboat can travel 24 miles downstream in 2 hours. It requires 3 hours to make the return trip. Find the rate of the boat in still water and the rate of the stream. So that's basically your rate of your current. So we have two things. We have the rate of the boat, which I'm going to call, let's call that R. And we have the rate of the current, or the stream, and I'm going to call that C. So, actually, let's not call that R. Let's call that B. And then the rate of the current is this. Now, I don't want to call that R because I've already got an R here, and that's going to make life a little hard, a little confusing. All right, so let's talk about downstream. Are we okay with the idea that if your boat is going downstream, the current is helping the boat, right? And since the current is helping the boat, right? So if the boat can go 10 miles an hour and the current is 2 miles an hour, the effective rate that the boat's moving, it'll be 12 because the current's helping. So in this problem, if I'm setting up for going downstream, I'm going to say that it's going to be the rate of the boat plus the rate of the current. Now, as far as going upstream, the current is hurting the boat. So you got the rate of what the boat can do by itself, but then you're going to have to take away because the current's subtracting because we're going against it. So going upstream, this is going to be B minus C. Well, now we read the problem and we plug in what we know. It says a boat can travel 24 miles downstream, so my distance is 24 in 2 hours, and it tells me that happens in 2 hours. The next sentence, it says 3 hours to make a return trip. So, if you think about it, if you're going downstream, the return trip means you're going upstream, so the current's hurting you. And it says that's going to take 3 hours. Well, it's the same trip, so my distance is going to be 24. Now, if this looks like our investment problem chart and our mixture problem chart, except it looks like they're investment because how you set up, the reason I use this particular chart is it works just like the other ones. Remember our little phrase at the top where it was rate times time equals distance? We've got our two equations. The first equation is going to be this times this equals this. Our second equation is this times this equals this. So if I write those two equations down, I'll have 2 times B plus C is equal to 24. And then I'll have 3 times B plus B minus C is equal to 24. See, if I set up my chart, I've got my two equations. This times this equals this, this times this equals this. Now I solve. Now, a couple of ways you can solve this. I mean, I guess technically I could multiply by 2 or I could multiply by 3. But I'm a big fan of how do we make this as simple as possible? And how we can make this as simple as possible, how about I take this first equation and divide both sides by 2. So now that first equation becomes b plus c is equal to 12. And if I take the second equation and divide both sides by 3, that's going to give me b minus c is equal to 8. Now I have something that's, if I use elimination, I end up with a pretty nice answer. If I just add these together, the c's cancel out. That's going to give me 2b is equal to 20. So the rate of the boat is 10. And if the rate of the boat is 10, I'd plug it back into one of these others, and I'd find out that the rate of the current is equal to 2. And at a very basic level, this is how rate problems work. You set up your chart. Your chart's going to have two situations. You're going to basically something where the wind or the current is helping, so that's going to be b plus c. You're going to have something where the wind of the current is hurting, so that's going to be b minus c. They're going to give you the time, and they'll give you the distance, and once you fill out your chart, you get your two equations by going this times this equals this. There's one equation, and this times this equals this. All right, now, what I want you guys to do, and this was left over in the homework from yesterday, you have where did my, it's over here. I want everyone to, you can look at the homework from yesterday in OneNote, or if you had trouble getting that, it's in the files with that massive homework sheet. You're looking for the rate problems. I want everyone to go, and I want everyone to set up your chart for problem 1. And then raise your hand when you've done that.
Why did you use b plus c as
downstream?
Why did you put that in?
Well, so think of the effective rate of the boat. Okay? So the boat by itself, if it's just with no current impacting at all, it's got a certain rate. But if you put it in the water's got a current, so the current is helping. So when you're going downstream, the current's helping. So B represents the rate of the boat, and C represents the current. So then I'll have, going downstream, I have to add the rate of the boat plus the rate of the current. And I need that so that when I talk about upstream, I can talk about how the current's hurting the boat, where you get the B minus C. Does that make sense?
Yeah, it does.
Okay. All right. So I need everyone to set up problem 1.